In this video, we're going to be continuing our discussion of chemical kinetics, and today we're going to be studying collision theory and activation energy. So, collision theory, this theory states that reactant species, which include atoms, ions, or even whole molecules, must collide with each other at sufficient speeds to interact or react with each other. Now, there are two possible outcomes of collisions between molecules. One outcome, which is the outcome that is generally undesired, is that molecules will just simply bounce apart and therefore have no reaction when they collide at low speeds, which refers to a low kinetic energy of the molecules in a sample. However, the second outcome, which is the outcome we're going to look at today, is if these collisions are sufficiently energetic, a reaction can occur, where the EK is greater than or equal to the activation energy, which we'll also get into in a bit. But for now, let's just consider this. So before we go any further, I want us to first review the basic idea behind the chemical reaction, which just refers to the breaking and forming of breaking of bonds of reactant species and rearranging or creating new bonds to yield the products. Okay, that's just the sole fundamental idea of chemical reactions. Okay, so with this in mind, let's go through the criteria for chemical reactions to occur based on collision theory. Okay, so for a reaction to occur, the molecules must first collide. The second is that collisions must have the correct steric geometry, or the collisions must be such that the molecules will collide in the correct orientation. So when I say correct orientation of colliding molecules for a reaction to occur, I'm essentially referring to the way the molecules are positioned so that they can interact effectively upon collision. So say for example, we have a hydroxyl group or OH with the oxygen having a negative charge. It'll be reacting with the with CH3Br where the oxygen is attracted to the partially positive charge of the carbon atom here. So we can see here that in this example, electrostatic forces are oriented in a way that attract the two molecules together and accelerate momentum or collision of molecules, allowing for a reaction to occur. So this is just a further example that elucidates on the concept of collision geometry. So we can see here that for reactions in A and B, we can see here that the molecules are oriented favorably that allow a reaction to occur, right? However, we can see that in reaction C, that no reaction occurs due to the incorrect geometric orientation, okay? The third criteria is that the EK must be at least equal to the activation energy. So collisions must occur with enough kinetic energy to allow interactions between reacting species, valence shells, so that electrons can rearrange and form new bonds, therefore yielding products, right? That's the third criteria. Oh, I also forgot to mention, so I didn't get to finish on the second criteria, so we can see here that in this formula here, that for the second criteria where collisions must have the correct steric geometry, we can see here the formula for the Arrhenius equation for activation energy, where K equals A times the exponent to the power of negative EA, or the activation energy, over RT, right? We'll get into that details about those, but just for now, I want us to take a look at this particular variable, which is the Arrhenius constant, right? Which is just equal to Z, the collision frequency Z, times P, which just refers to the proportion of molecules that are colliding at the correct impact angle, which just refers to the correct orientation of the molecules. So just keep this formula in mind. It's not necessary to understand, just an idea that better elucidates the concept of the Arrhenius constant. Okay. And then lastly, we have the fourth criteria, where the reaction rate is directly proportional to the number of collisions over time, right? And this makes sense, right? The reaction rate will increase as the number of collisions increase over as the ratio for collisions over time increases, because the number of collisions increases the frequency of reactions occurring between reacting species, which therefore increases the overall reaction rate. Right? So with these four criteria in mind of the criteria for chemical reactions to occur based on collision theory, we can get into the concept of the of the Arrhenius equation, right? Where savant August Arrhenius, the creator of the Arrhenius equation, introduces the concept of activation energy, where the activation energy is the amount of energy needed for chemicals to react to yield products. And by react, I mean break bonds, collide, rearrange, or form bonds, right? So this is the formula that we need to be familiar with, where the natural logarithm of the rate constant K equals the natural logarithm of Arrhenius constant minus EA, activation energy, over RT, which is also the same formula that I had shown previously above if you take away the logarithms, right? Where if I add an exponent to everything, we can see that this is the other way to express the equation, right? Where K equals A times the exponent to the power of negative EA over RT, right? Now let's define these variables. R equals the universal gas constant, which is 8.3145 joules per Kelvin per mole. Yeah, joules per Kelvin per mole. I'm pretty sure that's the formula. Just 1 second. Gas constant. Yeah, joules per Kelvin per mole. Right. I should fix that. And then T equals the temperature in Kelvin. So you have to make sure that the units are correct, where or are consistent, where temperature is always expressed in kelvins, especially in this equation here, okay? This is super important. In Kelvin. The activation energy is expressed in joules per mole. The Arrhenius frequency factor, which I explained above, is just comprised of the collision frequency and the fraction of the correct impact, the fraction of molecules colliding at the correct impact angle, right? And K is equal to the rate constant, okay? Now, when choosing to use one of these two forms, generally speaking, this form here, right here, is used for graphs where we want to plot the natural logarithm of K, which is the y variable, against 1 over the inverse of 1 over the inverse function of temperature, which is X, for activation energy equations. So here's the graph. This is the graph where ln K is y, the inverse of temperature is X, and the slope is negative EA over R, right? The slope is equal to negative EA over the universal gas constant, and then the natural logarithm of A is the y-intercept. So together, we find that these are the variables that make up this graph, right? And we can see here that when you put it in forms of y equals mx plus b, we get the exact same formula that I showed previously, which is this one. Okay. Now, I just want to draw our attention over to the Maxwell-Boltzmann distribution curve. So occasionally you may be tested on the concept of the Maxwell-Boltzmann distribution curve, and you just need to know exactly what it's used for. So the Maxwell-Boltzmann distribution curve is a graph that's used to show how many molecules, or the proportion of molecules, have the required activation energy to participate in reactions. So let's consider the variables here. So the y variable refers to the proportion of particles with a specific kinetic energy, or an arbitrary kinetic energy, or Ke. And we refer to this variable as n. Okay. X just refers to the kinetic energy, right? Now, from this Boltzmann distribution curve, generally speaking, when we see that there's a highlighted area over here, we can identify that this is just refers to the proportion of particles that have in a sample that have enough kinetic energy to react. So we can see here that the boundary here, that this particular boundary here is the activation energy, which refers to an energy boundary that, or an energy threshold that molecules need to achieve before they can react in a before they can participate in a reaction, right? And then this area here just refers to the proportion of molecules that don't have the activation, that don't have enough energy to participate in a reaction. So we can just essentially deduce that Ek here is less than Ea, the kinetic energy, for the proportion of molecules here. And then we can deduce that the activation, that the kinetic energy here is greater than the activation energy, right? It's important to note, very important to note, that because the kinetic energy of the molecules is greater than the activation energy, we know that they'll have enough energy to participate in the reaction. So this is the proportion that is able to participate in the reaction, okay? Just some other metrics that we may want to consider here. So the peak of this curve, the peak of the Maxwell-Boltzmann distribution curve, which refers to the mode, right? Which refers to the highest frequency or proportion of particles with a specific kinetic energy, right? And then the mean, which is situated between the mode and the activation energy, just refers to the average proportion of particles with a specific kinetic energy, right? Okay. Now it's important to highlight the relationship. So for this graph here, I think this graph will best elucidate the concept. We can see here that the proportion of molecules that are the proportion of molecules having enough energy to react, right, is directly proportional to T, the temperature. So we can see here that in this graph, right, we can see that as at higher temperatures, the proportion of molecules having the required energy for the reaction, right, is greater at higher temperatures. So N is directly proportional. N proportion molecules with Ek greater than Ea is directly proportional to temperature. Whereas at lower temperatures, we can see that the proportion of molecules with the kinetic energy, with their kinetic energy greater than Ea, is less. So generally, at higher temperatures, we can expect a higher proportion. And remember that with a higher proportion of molecules, with high kinetic energy, we can see that there's a greater number of collisions, which increases the frequency of reactions occurring between reacting species, and therefore increasing the overall reaction rate. Okay, so let's just connect this concept here, right? Where this number of successful collisions based on the kinetic energy being greater than the average energy is directly proportional to the temperature. So with higher temperature, we can infer that there will be higher reaction rates. Okay, so that's just essentially the importance of this distribution curve. Okay, all right, so with everything we've discussed, let's go through two key sample questions that I think will be helpful for learning how to answer these questions. So the first example, we're going to solve an activation energy question for a reaction occurring at two different temperatures. So there are two ways to answer this question, or two formulas that can be used to answer this question. They're both very similar. The first one is ln the natural logarithm of the ratio of K1 over K2, which is equivalent to the activation energy over R times 1 over T temperature 2 minus 1 over temperature T1. Okay. The second is the natural logarithm of the ratio of K2 over K1. It's different this time, which is equivalent to EA over R, where 1 over T1 minus which is equivalent to the activation energy over R times the inverse of temperature 1 minus the inverse temperature of T2, right? Generally speaking, I prefer to use this one, as I've experienced less calculation errors when I use this formula. So this is just a suggestion, but by all means, if you want to use this one instead, go for it. In this example, I go through both methods. But generally speaking, when you go through these questions, you always want to line up the variables first to determine K1, K2, T2, T1, right? And so on and so forth. So for this example, the hydrolysis of sucrose to yield glucose and fructose has an activation energy of 108 kilojoules per mole and a second order rate constant at 37 degrees Celsius of 1 times 10 to the negative 3 inverse molar concentration, or liters per mole per second. Okay, so it's asking what will the rate constant be at a temperature of 35 degrees Celsius. So from this question, we understand that at the same reaction is occurring twice at two different temperatures, and it wants us to find the rate constant at a temperature of 35 degrees Celsius. So with this, let's define the variable. So K1 equals 1.0 times 10 to the negative 3 inverse molar concentration per second, right? Or liters per mole per second, right? T1 equals 37 degrees Celsius, which is equivalent to 310 Kelvin. Now remember that we will always want to express temperature in terms of Kelvin for the Arrhenius equations. So use this formula where K equals Celsius, the degrees in Celsius, plus 273, right? And T2 equals 35 degrees Celsius, which is equal to 308 Kelvin, okay? And then the activation energy is equal to 108 kilojoules per mole. Well, we want to express it in joules per mole, so we multiply this number by 1,000 joules to express the activation energy in units of joules per mole, which is 108,000 joules per mole. Okay, so with the correct units in mind, we can then apply the formulas I had previously shown above, right? So we'll go through this formula first, right? Where the natural logarithm of the ratio of K1 over K2 equals the activation energy over R times the inverse of T2 minus the inverse of T1, okay? Now, from here, we want to make sure that since we're isolating for K2, we want to essentially multiply both sides by K2. So essentially what I did here to transition to this step is multiply both sides by K2. Oh, no, actually first, what we want to do is get rid of the logarithm. At least, because ultimately what we want to do is isolate for K2, right? So we want to isolate for K2. So what we need to do is we need to remove this natural logarithm by applying the exponent on both sides. So e to the power of x, which cancels this out, or apply the natural exponent on both sides, which cancels this out, right? And then what we're left with is the ratio of k1 over k2, which equals the natural exponent to the power of ea over r times the inverse of t2 minus t1, the inverse of t1, right? And then essentially I multiply both sides by k2, right? But divide both sides by e to the power of a over r times 1 over t2 minus 1 over t1, right? Which cancels this out, right? And then apply the same thing here, right? Which gets us this formula where k2 equals k1 over the natural exponent to the power of ea over r times 1 over t2 minus 1 over t1, right? And then from there we can just simply plug in the values where but what I preferred to do actually was first solve for this equation here. I wanted to solve for this first because this is a very it's a pretty elaborate calculation, so I decided to solve for this first, right? And then so 108,000 joules per mole over the universal rate constant times 1 over 308 minus 1 over 310, right? T2 and T1, right? Which gets us a certain value, right? Which is approximately 0.272, right? So 108 divided by 8.3145 times 1 over 308 minus 1 over 310 108,000 divided by 8.3145 times 1 over 308 minus 1 over 310 which should get us 0.272. Sorry, just 1 second. I'm plugging this into my calculator as well as I solve this. 0.8000 3145. There we go. Approximately 0.272, right? And then I apply whatever answer I got here. Just make a note. Apply exact number from calculator into e to the power of x. Right? we want to apply the exact number. Don't just round it up yet, right? Just make sure that you apply the entire number from the calculator, right? So e to the power of this answer, so e to the power of answer equals 1.312, right? But we're not done. 1.0 times 10 to the negative 3 divided by answer equals 7.61 times 10 to the negative 4. However, we did want to consider significant figures, so 7.62 approximately. Yeah, because there's 3 sig figs, right? 7.62, right? Oh, no, it's 2 sig figs because the rate constant is 2 sig figs. Yes. So it's 7.6 times 10 to the negative 4 inverse molar concentration per second, right? So essentially, I was just plugging in plain numbers here. Now we can apply the same. We can apply the same values into the formula, where essentially we have a bit of the same thing, where essentially you remove the logarithm by applying the exponent on both sides. I just kind of simplify the process this time, where I refer to x as this EA over R times the inverse of T1 minus the inverse of T2, right? And then I instead isolate for K2 by multiplying both sides by K1, just to simplify my calculations. At least for this particular example. In some cases, you might want to find K1, and therefore the other formula may be better. But generally speaking, I use this formula instead, where I want to just simply multiply both sides by K1, right? So the same formula applies, which equals, where we'll get very similar values, and then ultimately we round it down to 2 sig figs times 10 to the negative 4 inverse molar concentration per second. So both of these formulas should get you the same value. Lastly, we may want to consider solving activation energy equations or questions using graphical data. So in this example, for this question, we want to determine the activation energy and the Arrhenius factor constant. So what we're given is the temperature in Celsius and the rate constants. So for the first step, oh man, I don't think you can properly see these numbers. So for the first steps, you want to, hold on, let me fix this. So for the first step, you want to convert the temperatures in Celsius into Kelvin and find the inverse temperatures, right? Just give me a second while I try to fix this. Oh, it's a picture. I apologize, everyone. So essentially, I just convert the temperatures. I'm not sure if you can properly see these values, but essentially you just convert temperatures in Celsius to Kelvin, and then you find the inverse of those temperatures, right? And then you also want to find the natural logarithm of K. So you want to apply the natural logarithm to K for all of these rate constants. So let me just clarify. Apply ln to K, and then here convert C to K, and then apply 1 over t. Okay, sorry about my handwriting, it's a bit messy right now with the surface glitching out, but essentially you want to find ln k, and then you want to plot these values on a graph, right? You want to plot all the values on the graph where ln k is y and 1 over t is x, right? And then what you want to do is use the slope formula where negative EA equals the slope, negative EA over R equals the slope, right? Times the universal gas constant, right? So we find that the slope is equal to 10688, right? And then we want to multiply that number the negative slope by the gas constant, right? Which is negative times, yeah, oops, I kind of, the slope is negative 0.6, it's negative 10688. So negative 10688 times negative, the negative symbol, times 8.3145 equals 88,865.376. We want to round this to how many sig figs? We would want to round this to 3 sig figs, right? 688 are considered significant figures, so we want to round this to 3 sig figs. So 9.00 times 10 to the power of 4 joules per mole is equal to the activation energy, okay? Right? And then lastly, step 5. So we want to find the Arrhenius constant using the y-intercept. Now, ln A equals the y-intercept, right? And in this case, we found that in the example here, that the y-intercept is 26.533, right? The natural logarithm of A equals the y-intercept. So what we want to do is apply the exponent on both sides, right? Right, so that we can isolate for the Arrhenius constant, which is A, which is equal to e to the power of 26.55, which is approximately equal to 3.39 3 sig figs, right? 3.39 times 10 to the power of 11. Let me just check just to be sure. E to the power of 26.55. Yeah, 3.39 times 10 to the power of 11. I apologize for my handwriting, but I hope that clarifies things. Okay, and that's essentially it for these examples here. Okay.